So we have to make sure that we all are familiar with the definition of pH. And so let's write a generic expression for an acid dissolving in water, right, reacting with water. So HX plus H2O goes to hydronium and X minus. Um, and so how pH is defined is it is just the negative log of the concentration of hydronium ions in an aqueous solution. You can rearrange this expression if you want, and that will give you that the concentration of hydronium ions is equal to 10 to the minus pH. You know, in actuality, you don't need to use this word pH. For a while in the late 1800s, early 1900s, people didn't do this, but it's just convenient to work on a logarithm scale. So this P nomenclature just means negative power of, basically. Um, so that's the definition of pH. Pretty straightforward, but you know it's something just to make sure that you're wrapping your mind around correctly, because it's this negative power. What does that mean? You know, you should be able to tell me very quickly um, how many times more protons are there in a solution with pH 5 versus pH 6? And the answer is 10 times more, right? It's a logarithmic scale. So for every pH unit, that's worth a factor of 10. Another question, you know, you could think about is like, how many times more, or how many times less protons are there in a solution that is pH 9 versus pH 7? And the answer would be 100, right? 100 times, there's 100 times less hydronium ions or protons in a solution with pH 9 versus pH 7. Why? Well, because we went up on the pH scale going from 7 to 9, and we went up by 2 pH units. So it's 10 to the 2. So you got to put 2 zeros on after a 1. Acid and base strength. So again, here we have our equilibrium expression in a generic form for an acid. And we can define an equilibrium constant. That's just the concentration of H3O plus times, so products over reactants, right? Raised to their coefficients. All the coefficients here are 1. You'll notice we don't have water in this expression. I'm not going to, you take some explanation to get into that, but and your textbook doesn't, but some general chemistry books do an okay job at explaining it. If you're curious, I'm happy to talk to you about why water isn't in this equilibrium expression. But there's the expression. And so we can define something called the pKa. So again, P just meaning the negative logarithm of something. And so pKa is going to be negative log of Ka. And so a higher Ka means a stronger acid, and a lower pKa also means a stronger acid, but now we're on a logarithm scale. Just like a lower pH meant that there's a higher concentration of protons. We can do the same thing for a base, right? So we have a generic expression here, B for base. Base is, of course, a proton acceptor according to the Bronsted definition. So we're going to form HP plus and hydroxide. And write out an analogous expression again without water in this expression. And we can define something called pKb, which is again just the negative logarithm of something, so negative log of Kb. Similar sort of logic here. A higher Kb means you have a stronger base, and a lower pKb means you have a stronger base, again on the logarithmic scale. So one important property of any solvent that can support an acid or a base is that they, Bronsted acids or bases at least, is that they undergo what's called autoprotolysis. A little bit hard to say. And that is the idea that basically two water molecules will you know, you're doing this hydrogen dynamics, these proton dynamics, these proton transfers are occurring very fast on a very fast time scale, reaching equilibrium. But two molecules of water will essentially be constantly interchanging to give you the hydronium ion and the hydroxide ion. And this is kind of sets up, the boundary conditions, as we'll see later on in the chapter, of how water works and how it can facilitate acids and bases. But so we can write a equilibrium expression for this, again, without water in the expression, products over reactants. Well, if we don't have water in there, we don't have products. So it's going to be concentration of hydronium ions times by the concentration of hydroxide ions. And experimentally, you can actually determine what this value is. It's 1.00 times 10 to the minus 14th, okay? And so if we solve for x, where we know we have the same number of moles of hydronium as hydroxides, because they're both one coefficients here, put an x here, that becomes x squared equals kW. Take the square root of that, you're going to get 1.00 times 10 to the minus 7th to solve for the concentration of hydronium ions in pure water. This is at 25 degrees Celsius. It varies a little bit based on the temperature. So then you can take the pH of that and find that the pH, right, is equal to the negative log of the concentration of hydronium ions. So the pH of 100% pure water at 25 degrees Celsius is 7. So that's what we call pH neutral, just pure water. Okay? pH of pure water is 7. Now, what is the pH of tap water out of your sink or bottled water? Usually it's not actually 7, okay? Usually it's between 6 to 9. Your textbook says that this is due to, actually your textbook is wrong in what it says, okay? Textbooks are often wrong, it's okay. Your textbook actually says that it's always acidic, which isn't true, okay? And our water here in Reno is actually slightly basic. I believe it's around 8, and I'll tell you why in a second. But why does the book say it's acidic usually is because dissolved CO2 from the air goes into the water, and that will make carbonic acid, and so that's acidic. Now, depending upon where you're getting your water from, there's all sorts of things that can be in water. And those things can be from natural sources. Usually it's different ionic compounds, but also different organic compounds are in there. These are different minerals in the water, right? If you're drinking spring water versus, water in the Midwest, they'll have very different chemical compositions and tastes. Also, how the water is treated really affects its composition, affects its taste, and it affects its pH. And so, here we're extremely lucky. Remember, we are essentially drinking Lake Tahoe water down here in Reno. There is some sediment that does build up as the Truckee River flows. And there's a water treatment plant in kind of on the edge of Reno by 4th Avenue that takes the water in. But there is some sediment that builds up, but generally not that much. Essentially, we're drinking Lake Tahoe water. And Lake Tahoe has some of the cleanest water in the world, definitely some of the clearest water in the world, but also cleanest. I've heard that a lot of the metrics of Lake Tahoe water are actually far exceed what the EPA, Environmental Protection Agency, says is necessary for you to drink clean water. And that sometimes they actually go, on some of the metrics, it can go into the water treatment plants and actually come out slightly dirtier on some metrics. Other metrics, when you're talking about bacteria and things that you got to get rid of to keep it safe for us. So it's good that we have water treatment, don't get me wrong. And I wouldn't advise, without filtering Lake Tahoe water, don't just drink it because of bacteria, right? But on some of these other metrics, like totally dissolved solids, it's actually better than what the EPA requires before it's being treated, which is kind of amazing. Why is it so pure? Well, it's mostly snowmelt. That's one, right? It's basically all snowmelt and some rainwater. But the main reason is that it's in a granite bowl, essentially. And granite is a fairly inert rock and doesn't leach out many minerals into the water. So it leaves the water very pure. Here's a nice dorky picture of me at the Reno water treatment facility. And so it's pretty interesting, goes through all the different stages of water treatment, but they use these huge tanks of bleach in part to get rid of the bacteria. And that's part of the reason why our water is basic. It's just the chemicals that they chose to use, sodium hypochlorite, make the water a little bit basic. So again, I think we're around pH of 8. Last thing to think about for this video is how does Kw, right, that autoprotolysis constant, relate to Ka and Kb, the strengths of acids and bases respectively. So again, we have this generic expression for an acid, HX, and here is our equilibrium constant for what Ka is, right? We went over that. We can write a very similar thing, but now what I'm doing is I'm using the same sort of, I'm using the conjugate base, okay? So the conjugate base, and thinking about how that conjugate base could react with water and make hydroxide NaHX. And so I can define the Kb as, again, the products over the reactants without water in the expression. And so we know that basically the Ka describes this equilibrium, and the Kb describes this equilibrium where we have hydroxide. If you add these up together, well, what happens? You have HX on one side, HX on the other side. Those go away. And you have X minus on one side, X minus on the other side. Those go away. You end up with that autoprotolysis expression, okay? And so that is what Kw is. And so you may remember that whenever you add up chemical equations and you're tracking their equilibrium constants, you multiply them, okay? So this is basically a little bit of a short proof of why Kw is equal to Ka and Kb. So what this allows you to do is that, you know, if you know Ka, you can always find the Kb. You can find the Kb of its conjugate acid. If you know Kb, you can find the Ka of the conjugate acid. Sorry, if you know Ka, you can find the conjugate base. You can find Kb. Just would go Kw divided by that, right? You can also take the p's of all these, and that gets you pKa plus pKb equals pKw. pKw equals 14 because 1.00 times 10 to the minus 14 was Kw. Why is it a plus here, not multiplying? That's a logarithm rule, right? If you take a logarithm of a product, there's a mathematical rule. Mathematically, what that ends up being is addition.